Okay, now let's start with the last part about the clustering part. It's not really clustering, but it's kind of related to the k-means. Although we will work on simpler examples based on very familiar Bernoulli distribution. So the topic we are going to talk about first is the EM algorithm. So EM algorithm is a very well-known algorithm, and of course, we'll be looking at simpler versions of it, but for complex models, it can still be used. It's actually very popular before the deep learning era because as long as you have, for example, one of the three scenarios, you can actually use the EML algorithm. So the first is actually missing data. So we are looking at the second one is the latent variables. Really depends on from which perspective you are looking at the problem. Sometimes they are kind of similar. So we want to distinguish them further here. But and the other last category that EM might be used for is that the problem itself does not involve missing data or latent variables, but by using by over parameterizing the problem, like adding a new variable, which is where actually we think the variable is actually latent, and the optimization problem might be easier. Okay, but again, we will actually just focus on the most common case for the EM, where we are dealing with essentially latent variable models, um, and you will see some examples later. And the general idea that directly trying to do the parameter inference, trying to find the best parameter, is going to be hard, and we are going to use EM to do the task. Okay, so the first part is to start with some preliminaries. So we actually need to talk about the so-called EM function. Okay, so this kind of EM, convex function essentially is a special kind of function. And in the area of mathematic optimizations, convex functions are very useful because they are actually more general than linear functions, but they kind of are easier to deal with than most of the other functions. Okay, so if you think about in terms of functions, just think about one variable, right? The simplest function is a constant function, so it's a constant, right? So no matter you want to do minimization or you want to do whatever things, it's easier. Then the next simplest function is arguably the linear function, and we already talked about linear algebra, right? So not all the relationships are linear, and we need to have, different kind of shapes. So basically, what we can generalize from linear function is that it's a so-called convex function. So a convex function is defined as follows. Okay, so um, the definition is essentially here. Uh, essentially, yeah. Actually, this is if only if. So basically, it's a function f, and um, if you take any 2 points x1 and x2 for any two points within the value domain, which is AB, right? That's the domain. Otherwise, I mean, outside domain, the function is not even well defined. So what you do is that you actually try to find another one. You can think about this is x3, okay? So this is x1, x2, and this is x3. So you can see that x3 is actually somewhere in between. And the convex function essentially says the function value of this guy, right, is smaller or equal to this complex expression. Okay, so this complex expression. Okay, the expression here has a very intuitive geometric meaning. It's actually the fx1. This is x1, so this is fx1. Right, this is fx2, and if I want to find lambda, I mean, if you want to find a point which is on the linear line, which is actually on this line, and basically it's going to be on this one for a particular lambda. So any point, let's say for this point here, okay, we'll put it in this way. For example, if let's look at lambda equal to 1.0. Yeah, by the way, lambda is actually a number between 0 and 1. So that's the mix-up kind of percentage. So lambda equals 1.0, it actually means the whole right-hand side is actually fx1, right? And lambda equal to 0, it's actually fx2. So basically, you can imagine that as lambda change from 0 to 1, basically the points actually move towards the first point. And that's actually the same thing on the x-axis here, on the way you obtain x3. So in other words, if you have the animation, you can actually imagine that whenever you actually move to here, you actually do the drop down, and you can have an intersection. Basically, you actually drop down, you actually find the x3 here. That's actually also the lambda. So basically, there is another line going from here to here. That's also lambda, right? Lambda, which is from 0 to 1 as you move to the left. Okay, so basically this is the f lambda x3. So basically that's the right-hand side. Okay, so all these kind of explanation trying to convince you that the convex function essentially says, okay, if you, for any 2 points on the line, if you draw a linear line, and any of the points on this line is larger than the corresponding points on the function. So the function value is actually upper bounded by the 2 ends. Okay, so if you think about this, actually is kind of similar to the triangular inequality we talk about in the clustering part, where we actually can make sure that even if I don't observe some of the distances between any 2 objects, but as long as I have some kind of partial information, I can derive a bound on the value. Okay, so here that's the same thing. So there are other alternative versions of definitions. If the f is actually a continuous function, let's say it's at least twice differentiable, then basically you can actually imagine that. So again, this is one dimension, but multi-dimension, that's the same. So if this is f, right? So f prime will actually be the tangent line. So at any points, let's say if I remove this one, this is actually, let's say I call it x3, that's going to be f prime evaluated at x3, right? And if you look at this line, it's actually going to be here, right? Okay, so basically, you can actually see that the equivalent definition when f is twice differentiable is that the function, the second derivative of the function, is always greater or equal to 0. So in other words, if you think about this, is if f is the trajectory, right? F prime is actually the velocity, and f double prime is the acceleration. Right, so this is actually means that maybe the car currently is at negative, let's say, coordinates in terms of the trajectory on one dimension. But as long as the acceleration is actually positive, it's eventually going to become moving towards the positive direction, right? So that's the equivalent solutions. And again, this is convex function, but we also have convex set, and if you think about most of clustering algorithm, will also give us convex shape, this kind of cluster. Convex set is actually defined in a very similar way. This is not convex. Basically, this kind of shape, probably not. Yeah, the simplest one is that you can actually see that if you have all these kind of lines, if you do the intersection this will actually define all the half plane, intersection of the half planes will actually give you convex regions, okay, or convex set, or I mean there is no intersection, right? So basically, the it's kind of similar in the sense that if you have any 2 points, and if you draw the line, every point on the line is within the set. So that's the convex set. So in terms of the optimization and in machine learning, if the problem is actually convex, it's very good. Okay, this is because later we are going to do some kind of optimization. Usually we call it minimization. Mathematically, usually we do minimization. In the problem we are going to deal with, we want to do maximization. But if you use some kind of library, you can always take the function. Let's say if you want to maximize function f, you can actually minimize the function minus f. Right? So why this is actually useful? Okay, so just take this one-dimensional example. Right. So if I want to find the minimum point on this f, it's very easy, right? So all you need to do is that you can actually start from anywhere, and then the gradient direction will actually be going up, right? So you actually decide to traverse in the opposite direction of the gradient, and because this is actually convex, there is only one, unique. So eventually you are going to, it's like a ball rolling. Basically, it's going to go down to the bottom, and that's going to be the not only the local minimum, but also guaranteed to be the global minimum. But instead, if your function looks like this, right, have several valleys, right? So then it's all depends on your starting position. So if you start from here, you actually will start from here. You actually will end up with this position, and if you start from here, you actually will end up here. Right? So trying to find the minimum points on this kind of non-convex function is actually very hard. It turns out that many of the functions are actually convex, although not all of them. And usually for convex functions, we have the problem is arguably much easier. So one of the important functions that are convex is actually minus log x. Okay, or in other words, we can actually say if fx is convex, minus fx is actually concave function. So for concave functions, this one actually becomes the other way around, right? So this is actually, if it's concave, then basically that's greater or equal to. Okay, so essentially log x is concave. So the previous definition is actually using two points, and then you do the interpolation. Right? So you can actually do multi-point interpolation as well. Okay, we won't go through the details, but essentially it can be proved using induction on this lambda i's. So all you need to do, essentially the conclusion is that the previous one is actually can be thought of as lambda I times xi. So if you have n points from x1 up to xn, so that's a concise way of saying all these kind of n points, right? So you have n points, and what you do is that you actually try to find all these lambdas such that sum of lambda I equal to 1.